Hi, folks. My project during this coronavirus time was to try to figure out the most beautiful equation in mathematics is what they call it. This one right in the middle. It's e to the pi I plus 1 equals 0. I didn't understand what that meant, and I've never understood it for decades, and so I figured that now would be a good time to figure it out. And I would know that I figured it out if I could explain it very clearly and easily to myself or to a viewer who didn't know anything about it. So a few weeks ago, I explained e to the pi I plus 1 equals 0 using a couple of areas that applied to it. Logarithms and what is the number e, 2.718. What is I, an imaginary plane, just how do some of those things work. I left a couple of these areas open because I didn't really understand them very well, sine and cosine and infinite series. So today I'd like to focus on how those areas explain this equation. Some of the more challenging areas I've had to spend a few weeks to figure out. So let's get right to it. Sines and cosines. Typically we think of them as triangles related to trigonometry. If you instead think of sines and cosines as circles, things moving around in a circle, it can kind of help your perspective. So look at this straw here. I'm spinning this straw around. Let's say that I put the straw so that it's facing right at the camera there, and now I turn it over here so you can see the length of this. Let's say that this is 0 degrees, and then as I rotate the straw, I'll rotate it through certain angles. So at 0 degrees, this is the length of the straw that you see. If I rotate it 1/6 of a semicircle, or 30 degrees, it's actually a little bit narrower now than it was before. If I rotate it 60 degrees, 2/6 of a semicircle, it's now about half, it appears about half the length that it was. Of course, we know it's the same length, but it appears about half the length. And then if I rotate it a full 90 degrees, it pretty much disappears. Now it's down to 0. So a length of 1, a length of here, it's about 0.886, 0.87. Here's about 0.5, and here's about 0, the original length. If I continue to rotate it in that direction, now it's this distance this way, negative 0.5, negative 0.87, negative 1. So I go from a length of 1 to a length of 0 to a length of negative 1. That's cosine. That cosine is the length of that leg through those angles. Now, if I rotated, we rotated our perspective and we looked at the straw from a 90-degree angle from some imaginary view, here it shows 0, even though we know from our perspective it's really a length of 1. So here it shows 0 from this perspective. And if I rotate it from this perspective and go from 0 to 90, there's a length of 1 right there in this imaginary perspective, and then continue to rotate 180 degrees, now it's back to 0 again. So those two perspectives are sine and cosine. On a piece of paper, here's what it looks like. You have cosine here, where we had the straw this way, and then we rotated it, and it went smaller, smaller, appeared to disappear, and then it got larger and larger, and that was negative 1 pointing this way. Sine in this imaginary direction that we looked at was like this, and then it got bigger and bigger, got to a length of 1, and then got back down to 0 again as it rotated. How this looks on a graph is like this, where cosine started out at a length of 1 and then shrunk down to 0. Sine started out at 0 and then went up to 1. And if we kept rotating it, it went around like that. If we put these two pieces of paper together, we can see how sine looks like this, and cosine looks like this. Okay, so if we add those two together, if I could take any one of these, but I'm going to choose this last one, this 180 degree turn. We were like this, and we turned it 180 degrees. So cosine was at negative 1, and sine was at 0. If we add negative 1 plus 0, we get negative 1. And that's at that 180-degree angle. I use the symbol pi here because when we talk about angles, you can talk about radians, and that's pi radians. So if you rotate something 180 degrees, that's the cosine of that angle plus the sine of that angle. From some other perspective, you'll be at negative 1. That's easy to picture. 1, 0, negative 1. That's it. So, cosine of pi plus I sine of pi equals negative 1. All right, remember that. We're going to use that in just a sec. The next thing I want to talk about is infinite series or Taylor series. And looking at this drawing here, if you want to go from home to your school, you could go in a straight line. That would be the best way to go. But unfortunately, there's no roads there, so you have to take a certain number of turns, left and right, a certain length, and then you'll eventually get there. So the best way to get there is straight, but really practically you need to break it up into tiny bite-sized chunks. This is what infinite series and Taylor series are dealing with. They're saying that we know if we have an equation that deals with cosine of x, for example, we know that the equation looks like this, or the graph looks like this, but this is hard for a calculator to calculate. When you program a calculator, you actually want to break it up into much tinier, many steps, of very easy steps. And if you make these tiny steps, you can approximate what that curve looks like in better and better regions. The more and more steps you add, the more and more little tiny turns you add here, the more accurate your final direction will be. So keeping that in mind, what they discovered years ago is that when you take a graph of, for example, cosine, and let's use the example of 180 degrees here, pi, cosine of pi, you can break it up into many little chunks, an infinite number of chunks, and that'll be easier for a calculator to calculate when you punch it into your calculator than just to try to figure out what this curvy line is. Similarly, you can do the same thing with sine, and you can find that it's this Taylor series is an approximation of sine. If you add the two together, you get this huge, long set of points that you can calculate that will be the same as this equation here, as this side of the equation here. So, looking at this weird-looking set of series of points here, if we remember this for just a sec, and then come up here. Here's a graph of e to the x. E is 2.7, and a logarithm is the way that you form every single number there is. So if we put any other number in x, 2.7 to the first, 2.7 to the second power, 2.7 to the third power, 2.7 to the fourth power, we can generate any number that there is. They found out many years ago that e to the x, the Taylor series of it, looks like this: 1 plus x squared over 2 plus x squared over 3 plus on and on and on and on and on. And then Leonard Euler was the first one who discovered, hey, wait a minute, this Taylor series looks very similar to this series here. The only difference is that this one has an I in it on some of these factors from that imaginary perspective that we looked at the straw from. So he's like, hey, if we add an I to this one, and he put an I there, and he factored it out, and he realized that these two were identical if you stick an I in here in the exponent. Cosine pi plus I sine pi is the same thing as e to the pi I. And since this, we know from earlier, is equal to -1, then therefore we know that e to the pi I equals -1. And what's that saying? That's saying is, as we rotate a number 180 degrees, as we rotate this straw 180 degrees, we'll be at the -1 point. If we rotated it 360 degrees, if this was e to the 2 pi I, that would equal 1. or we could rotate it several times around, and it would oscillate back and forth between 0 and 1 and -1, just like our graph over here shows an oscillation back and forth, So if we simplify, rearrange that, e to the pi I plus 1 equals 0, which goes back to our original most beautiful equation, e to the pi I plus 1 equals 0. That's all it means is what happens to the straw when you rotate it. So I hope this helps, and I hope this counts for my, my midterm exam result.